So you've opened the shoe factory and you're trying to figure out how many thousands of pairs of shoes to produce in order to optimize your profit. And so let's let X equal to thousands of pairs produced. Now let's think about how much money you're going to make per pair. Actually, let me see how much revenue, which is how much you're actually going to sell those shoes for. So let's write a function right here. Revenue as a function of X. Well, you have a wholesaler who's willing to pay you $10 per pair for as many pairs as as you're willing to give them. So your revenue as a function of X is going to be 10 times X. And since X is in thousands of pairs produced, if X is 1, that means 1,000 pairs produced times 10, which means $10,000. But this will just give you 10. So this right here is in thousands of dollars. So if X is 1, that means 1,000 pairs produced. 10 times 1 says R is equal to 10, but that really means $10,000. Now, it would be a nice business if all you had was revenue and no costs, but you do have costs. You have materials, you have to build your factory, you have to pay your employees, you have to pay the electricity bill, and you have to hire a bunch of consultants to come up with your costs, what your cost is as a function of X. And they come up with a function. They say is the number of the thousands of pairs that you produce cubed minus 6 times the thousands of pairs you produce squared plus 15 times the thousands of pairs that you produce. And once again, this is also going to be in thousands of dollars. Now, given these functions of X for revenue and cost, what is profit as a function of X going to be? Well, your profit as a function of X is just going to be equal to your revenue as a function of X minus your cost as a function of X. If you produce a certain amount, and let's say you bring in, I don't know, $10,000 of revenue and it costs you $5,000 to produce those shoes, you'll have $5,000 in profit. But this is just an example. This is what we're trying to optimize. We want to optimize P as a function of X. So what is it? I've just said it here in abstract terms, but we know what R of X is and what C of X. This is 10x minus all of this business. So minus x to the third plus 6x squared minus 15x. I just subtracted x squared. You subtract 6x squared and it becomes positive. You subtract the 15x, it becomes negative 15x. And then we can simplify this as, let's see, we have negative x to the third plus 6x squared minus 15x plus 10x. So that is minus 5x. Now, if you want to optimize this profit function analytically, the easiest way is to think about what are the critical points of this profit function, and are any of those critical points minimum points or maximum points? And if one of them is a maximum point, then we can say, well, let's produce that many. That is going to be, we will have optimized, or we will figure out the quantity we need to produce in order to optimize our profit. So to figure out critical points, we essentially have to find the derivative of our function, and figure out what that derivative equals 0, or when is that derivative undefined. That's the definition of critical points. So P prime of X is going to be equal to negative 3x squared plus 12x minus 5. And so this thing is going to be defined for all x. And so the critical points we're going to have is when the first derivative right over here is equal to 0. So negative 3x squared plus 12x minus 5 needs to be equal to 0 in order for x to be a critical point. So now we just have to solve for x. And so we just are essentially solving a quadratic equation. Just so I don't have as many negatives, let's multiply both sides by negative 1. I just like to have a clean first coefficient. So if we multiply both sides by negative 1, we get 3x squared minus 12x plus 5 is equal to 0. And now we can use the quadratic formula to solve for x. So x is going to be equal to negative b, which is 12 plus or minus the square root. I always need to make my radical signs wide enough. The square root of b squared, which is 144, minus 4 times a, which is 3, times c, which is 5. All of that over 2a. So 2 times 3 is 6. So x is equal to 12 plus or minus the square root of, let's see, 4 times 3 is 12 times 5 is 60. 144 minus 60 is 84. All of that over 6. So x could be equal to 12 plus the square root of 84 over 6. Or x could be equal to 12 minus the square root of 84 over 6. So let's figure out what these two are. And I'll use a calculator. I'll use the calculator for this one. So I get, let's see, 12 plus the square root of 84 divided by 6 gives me 3.5. I'll just say 3.53, so approximately 3. Actually, let me go one more digit because I'm talking about thousands. So let me say 3.528. So this would literally be 3,528 shoes because this in thousands are pairs of shoes. And then let's do the situation where we subtract. And actually we could look at our previous entry and just change this to a subtraction. Change that to a negative sign, a subtraction. There you go. And we get 0.4725. Now these are all we know about these, or these are both critical points. These are points at which our derivative is equal to 0, but we don't know whether they're minimum points. They're points at which the function takes on a minimum value, a maximum value, or neither. To do that, I'll use the second derivative test to figure out if our function is concave upwards or concave downwards, or neither at one of these points. So let's look at the second derivative. So p prime of x is going to be equal to negative 6x plus 12. And so if we look at p prime of 3.528, this is between 3 and 4. So if we take the lower value, 3 times negative 6 is negative 18, plus 12 is going to be less than 0. And if this was 4, it'd be even more negative. So this thing is going to be less than 0. So I don't even need to use my calculator to evaluate this. 0.47, that's roughly 0.5. So negative 6 times 0.5 is negative 3. That is going to be nowhere close to being negative. It's definitely going to be positive. So p prime of 0.4725 is greater than 0. So the fact that the second derivative is less than 0, that means my derivative is decreasing. My first derivative is decreasing when x is equal to this value, which means that our graph, our function, is concave downwards here. And concave downwards means it looks something like this. And so you can see what it looks something like that. The slope is constantly decreasing. So if you have an interval where the slope is decreasing, and you know the point where the slope is exactly at 0, which is where x is equal to 3.528, it must be a maximum. So we actually do take on a maximum value when x is 3.528. On the other side, we see that over here we're concave upwards. The graph will look something like this over here. And if the slope is 0, where the graph looks like that, we see that that is a local minimum. And so we definitely don't want to do this. We would produce 472.5 units if we were looking to maximize our profit, maximize our loss. So we definitely don't want to do this. Well, let's actually think about what our profit is going to be if we produce 3.528 thousands of shoes, or 3,528 shoes. Well, to do that, we just have to input it back into our original profit function right over here. So let's do that. So we use my calculator for this one. My original profit function is right over here. I want to be able to see that and that. So I get negative 3.528 to the third power plus 6 times 3.528 squared minus 5 times 3.528 gives me a profit of 13.128. So let me write this down. The profit when I produce 3,528 shoes is approximately equal to, or it is equal to, if I produce exactly that many shoes, it's equal to 13.128. So if I produce 3,528 shoes in a given period, I'm going to have a profit of 13,128. Remember, this right here is in thousands. This right over here is 13.128 thousandths of dollars in profit.